understand the concept of measuring uh, chemicals. We use a proper amount of ingredients, any kind of recipe that you take at home, and whether you're filling in your gas tank, you always need to know a certain amount of fuel will fill in your gas tank. So there is somewhat a kind of accountability with the ingredient measured. In chemistry, we use a term that is called as a mole. A mole is a very specific term that is used mainly. A mole is a term that is used mainly to understand what amount of substance is present. In other words, when we use the term dozen, a dozen implies to you that it's a number of 12, which means it could be a dozen roses, a dozen donuts, a dozen pencil. You understand that it's a collection term that is used to specify a certain number of an item. Similarly, another example that you can see up here is a ream of paper. A ream is always considered to be 500 sheets. A case quantifies a number 12. So these would be terms that are used to specify the number of a substance. In chemistry, we use the term moles to count very tiny particles. So we are either measuring or counting, I should say, atoms, molecules, or ions. Any of these tiny molecules or atoms or ions can be counted by, and the count is considered to be a mole. And there is an amount of what this count will be. This count of a mole is going to be a very large number, and that number is 6.02 10 to the power 23. So whether we are taking a mole of carbon atoms, which would mean that there are 6.02 10 to the power 23 atoms of carbon, or a mole of sodium atoms, or a mole of gold atoms. We can also use the term mole to count the number of molecules. So whether it's a carbon dioxide, which is a molecule, or a molecule of water, each will have the same number of molecules, which is 6.02 10 to the power 23. This collection is considered to be a value which is given to you up here, and this number is called as an Avogadro's number, based on an Italian physicist who calculated this very, very large number. So you can pretty much take out the decimal and see what a large number this is. So Avogadro's number is used for a collection of items, of atoms, molecules, or ion. So anytime you indicate a mole of a compound, then that will be considered that mole would be 6.02 10 to the power 23 of the particular type of particle that makes up that compound. Now, the mole over here, for example, in an ionic compound, here we have sodium chloride and potassium sulfate. So when you say a mole, it's going to have that many formula units of that particular compound. Now, a mole can also be expressed as an equality. So here is your equality that is written to you. A mole is 6.02 10 to the power 23. You can convert that into two conversion factors. We learned this back in the dimensional analysis chapter. So let's see how this problem is done. Up here, it's read as how many copper atoms are in 0.50 moles of copper. So notice I've placed 0.5 mole of copper up here, and then I times it to my conversion factor. Again, I have many times repeated that this unit over here has to match the unit on the bottom on your conversion factors. When those two happen, then you cancel these out, and now you're expressing the number of atoms present in 0.5 moles of copper. Now, using Avogadro's number, we can also convert particles of substances to mole. So, for example, a question reads, how many moles of carbon dioxide are present in 2.50 and 10 to the power 25 molecules of carbon dioxide. Notice I've done the same thing. I've got my molecules up here, and I've got my molecules on the bottom. In this particular case, I'm using this part of the conversion factor and setting it up to cancel my molecules and expressing my answer in the number of moles. In the previous example, let's go back and you can see up here I used this part of the conversion factor. Okay, now that we know what is a mole, which is a quantity of dozen apples or a dozen roses or a dozen pencil or a dozen cantaloupes or a dozen egg do not weigh all the same. So when you take a mass of a mole, then that is called as a molar mass. So that is a mass of 1 mole of any compound expressed in grams. And the way this is done is fairly easier. We usually use the atomic mass of an element to express that as a molar mass. So, for example, 1 mole of sodium would be equal to the atomic mass of sodium, which is 107.9, and you can round this off for this class purposes as 108. For carbon, then 1 mole would be 12 grams, and 1 mole for sulfur would be 32 grams. Fairly simple. So now imagine if I had asked you to go and get 2 moles of carbon dioxide or 2 moles of carbon powder. Now you can almost see up here there's a powder up here. 2 moles would have the quantity, if you do the count, then the count will be 6.02 10 to the power 23 for 2 moles. Actually, this is for 1 mole, so we'd have to almost, let me erase this. Okay, so 1 mole of carbon dioxide is 6.02 10 to the power 23. So if I want to do 2 moles of carbon dioxide, then I would have to set it up in which I have 1 mole on the bottom and 6.02 10 to the power 23 on the top. I cancel these out, and my value, if you do your calculation with your calculators, it should come out to, let me just do it up here. Which comes to almost like 1.2 10 to the power 24, I think, if I did my math correctly on the calculator. So it's a very large number. Now, it's very hard for you to count these number of atoms. However, it will be very easy for you to weigh 2 moles of carbon dioxide if you knew what 1 mole of carbon dioxide weighs. So, for example, carbon has an atomic mass of 12 plus 16 times 2 for oxygen. So that is 12 plus 32, which is going to be 44. That is 1 mole of carbon would be 44 grams. 2 moles of carbon would be 88 grams. So if you go and weigh 88 grams of carbon dioxide, then it's going to have that many large number of moles of carbon dioxide. Hopefully it is making sense to you as to what I'm talking about. We will take the quantity and convert that into mass and mass into quantity. So here is another example in which we see the molar mass of a compound that is shown to you is calcium chloride. And calcium, since there are 1 mole of or 1 atom of carbon, its atomic mass is 40. Chlorine, there are 2 atoms, so that each atom is 35. 35 times 2 is 71. 35.5 times 2 is 71. And the total will come out to 111 grams. So that is 111 grams of, would be the molar mass of calcium chloride. Now, let's look at formulas to understand clearly how to do our mathematical calculations. Now, in a formula that we have done, we've already studied that a subscript in a formula basically tells the relationship of how many atoms are in the formula. So, for example, this is a molecule of glucose, and you can see there are 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. We can also express that as 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. So if you took the total of this, which would be carbon I'm sorry, I accidentally went too fast on the, let's go back over here. Okay, so if we go back and now let's say 6 moles of carbon, you would have 6 times 12, and then you would take 12 times 1, and you would take 6 times 16. And if you total those up, that comes to 180 grams, which would be the formula weight for glucose. Now, subscripts we have learned are used for conversion factors. So if you really want to use, you want to say the relationship of the number of carbons per a formula, you can express that. So for example, here's a formula of aspirin. Aspirin is C9H8O4. So notice I've taken a relationship of 9 moles of carbon for every 1 mole of the molecule of aspirin, 8 moles of hydrogen for every 1 mole of aspirin, 4 moles of oxygen for 1 mole of aspirin. Or you can do it the other way. So pretty much we're going to complete this section over here in which we have learned how to calculate atoms or molecules. And the first thing to determine is look at the number of the number of moles that are required. Write a plan to convert moles to atoms or molecules, and use Avogadro's number to write a conversion factor. So let's try to do a problem up here in which we have how many oxygen atoms are in 0.15 moles of aspirin. What is given to us is we are given that this problem has 0.15 moles of aspirin, and what we need to find is the molecules of aspirin. So I tell students to read the question many times to see what you are required. It's asking how many atoms of oxygen are present in these many moles of aspirin. So you have to now come up with your plan. So for moles of aspirin, you need to know moles of oxygen from the formula, and then from there you will go to the atoms of oxygen. So let's look at the equality. The equality that we will use is 1 mole of aspirin has 4 moles of oxygen atom, as you can see from the formula. So these would be my conversion factor. And notice I wrote it down as 1 mole of oxygen is 6.02 10 to the power 23 atoms, because that's a standard value which we know. So now since we know all these 2 different factors, which is one set is this and one set is this. Let's go back. Remember, we have to convert moles of aspirin to the moles of oxygen first, and then from there you will go to the atoms of oxygen. So when you set up a problem, we want to do it in one step. So notice, now let's read it, 0.15 moles of aspirin. We're converting down to the moles of oxygen using my conversion factor. I keep the same unit on the bottom to make sure my units are converted to the moles of oxygen. And since I know 1 mole of oxygen is 6.02, again, notice these 2 are the same. So you will cancel this unit to this unit to this unit, and you convert your 0.15 moles to the oxygen atoms. We might do some problems in class too to reinforce these concepts. Hopefully you're understanding this. I think I'm going to stop here, and then we will do a second section in the next lecture.